All right. This is the third video in a series of 4 videos responding to your 321 survey on 5.4 curve sketching. You requested another example of a curve sketching with an asymptote. In the previous 2 videos, we found out everything we can about f and f prime. In this video, by the end, you should be able to find the second derivative and use that to find intervals of concavity and inflection values for my function. So just to recap, I'm going to use f in one of these problems to find out all the information I can about asymptotes, domain, and where the function crosses the axes. I'll use f prime to find critical values and relative extrema and places where my function is increasing or decreasing. And I'll use f double prime to find intervals of concavity and inflection values. So we'll be focusing in on this third step, f double prime, and we'll be finding intervals of concavity and inflection values for the function that we've been looking at. So we've been looking at x squared minus 4 over x squared minus 1. And what I want to do in this video is just find intervals of concavity and find inflection values. So if you'll recall, in the second video, we determined that f prime of x is equal to 6x over x squared minus 1 squared. Now, to find the derivative of this, to find the second derivative of f, I just take a derivative of the first derivative. And so again, by the quotient rule, I will have low d high minus high d low over the square of what's below. Low meaning x squared minus 1 squared, d high meaning the derivative of the numerator, minus high is the numerator, d low is the derivative of the denominator. So by the chain rule, this is 2 times x squared minus 1 times the derivative of the inside is 2x. OK? And so that's all over the square of what's below is x squared minus 1 squared squared, which is to the 4th power. So I realize this is sort of a silly rhyme to remember, but I was never able to remember the order here until I actually learned this rhyme. So low d high minus high d low over the square of what's below, and then I remember which one comes first. So we definitely want to simplify this. If you take a derivative, a second derivative of a rational function, you'll typically end up with this term being in common everywhere. So you can cancel some of these. So this is maybe to the 3rd power, this is to the 1st power, and that just cancels. After that, if you expand and try to factor this thing, you'll find that f double prime of x is equal to negative 6 times 3x squared plus 1 divided by x squared minus 1 to the 3rd power. OK, so in this form, it's a lot easier to find out where the zeros are and whether or not it's positive or negative. So for example, 3x squared plus 1 is never equal to 0. This is an irreducible polynomial over the real numbers. It's always positive, in fact. And when you multiply times negative 6, it's always negative. And so that actually tells us that there are no inflection values, because the only other places that I want to check for concavity switches are where the function is actually discontinuous. But I certainly want to check around plus or minus 1, and that's it. So concavity might switch at x equals plus or minus 1, because these are places where the function is discontinuous. And so like in the first example, I want to set up a table. We'll call this a concavity table. Just because if you're doing this all on one page, there's a lot going on. There are a lot of tables floating around. So I want to take an interval. I want to find a test point in that interval. And then actually, following the strategy that we did in the first video, instead of doing this all at once, and instead of having to plug into this function and use our calculators, let's just look at the numerator and the denominator separately. If I'm not going to use a calculator to graph my function, then I probably don't want to use one to actually find out what the sign of the second derivative is too. So I will look instead at 6 times 3x squared plus 1. I'll look at the function x squared minus 1 cubed. And then since my derivative is just the quotient of these two things, if I want to know what the sign of f double prime is, I'll just count the number of negative signs here. And so this will tell us concave up or concave down. So the intervals I'm interested in are negative infinity to negative 1, negative 1 to 1, and 1 to infinity. These are just places where I'm discontinuous. I'm going to be really careful here, and I'm going to draw now maybe a squiggly line here at places where I've chosen a point because it was a discontinuity. The reason is because later on, I don't want to falsely conclude that these are somehow points of inflection. So you can indicate this any way you like. I do it with a squiggly line or a dashed line, or at least just writing in the words that I chose this because it was a point of discontinuity. We want to choose test points here. -10 will be convenient to plug into things. 0 is nice if it's available, and 10. And so I just want to mentally plug into here without using a calculator. If I square a number, multiply by 3, and add 1, that thing's positive. Multiply by -6, that's negative. It doesn't have anything to do with what the number is. So this is always negative. X squared minus 1 cubed, this is where things are going to switch signs. So -10 squared is 100, minus 1 is 99. 99 cubed is some really big but very positive number. And I don't really care about what the value is, I just care that it's positive. 0 minus 1 is -1, cubed is still -1, so that's negative. And finally, on the last interval, if I plug in 10, 99, again, cubed is some large positive number, and so I know this thing is positive. And so now I can conclude things about the sign of the derivative. A minus divided by a positive is negative. Negative over negative is positive. And finally, negative over positive is negative. And so what are these? So negative sign on f double prime means that this thing is concave down. Then it switches to concave up because the second derivative is positive. Then it switches finally to concave down again. There aren't any points of inflection, even though I switch concavity here, because these happen at points of discontinuity. And to have a point of inflection, I need to have an actual point there. So we don't call these points of inflection, but they are places where my function switches its concavity. So there are no points of inflection. But I'm concave up on the intervals -1 to 1, and I'm concave down on the intervals -infinity to -1, united with 1 to infinity. Okay, so we were able to use the sign of the second derivative to determine everything we could about concavity and inflection values. In the next video, we're going to take all the information we learned about f, f prime, and now f double prime and combine this into one graph.